Hello everyone, welcome to another interesting lecture of digital signal processing. In today's lecture, we are going to continue your FIR design using Windows, and we're going to see another numerical. We're going to see about a bandpass filter using your FIR design. And in this numerical, we will be probably using a different window. So the last numerical we saw in the class was about high pass filter using your Hanning window. So here we will see your bandpass filter using Hamming window, and then I'll also show you the band stop filter. I'll just start the band stop filter, and I will leave the computation of the coefficients as a take home exercise for you. So the question is h of e to the power of j omega is equal to 1 from pi by 4 to 3 pi by 4, and your m is equal to 11. So that is what we need to do. So which means the range of your bandpass filter is from pi by 4 to 3 pi by 4. So as you can see, if the upper cutoff frequency in this case is 3 pi by 4, and whenever your upper cutoff frequency is equal to pi, your bandpass filter becomes your high pass filter. Got it? So this is an interesting analogy, and this is an interesting also question tested in interviews. Whenever your upper cutoff frequency is equal to pi, then your bandpass filter is equal to high pass filter. Okay, just remember that. So now the formula that we'll be using is from the Fourier series FIR equation. H of n is equal to e to the power of j omega n integral from minus pi to pi. So, and then we are going to multiply it with our Hamming window, and that is your FIR window design. And then we need to plot the magnitude response, and this is the formula I'm going to use for m is equal to odd and symmetric. So h of m minus 1 by 2 plus etc. This formula we have seen. So these are the three formulas you need to solve any problems in your exam, and mostly most of the exams, what I have seen is the questions are tested not on the even. It's very it may come. So you must know even and odd symmetric. However, the anti-symmetry, where you use the sign, is not a very common question. So just remember the magnitude response formulas for your m equal to even and m equal to odd. So in this question, your m is equal to odd. So which is what we'll be using. So we are using that formula I have shown. Now let's do the integral. Let's find our h of n coefficients from minus 5 to plus 5. So it's symmetry from minus 5 to plus 5. Because why we are choosing minus 5 to plus 5? Because in this question, if you see, your h of omega is ranging from minus pi to plus pi. So it is having the symmetry about the origin, right? About the y-axis, your symmetry is on the left side and the right side, because it's from minus pi to 0 and 0 to pi. So your FIR coefficients h of n will also have the same symmetry in the time domain from minus pi to 0 and 0 to 5. That is your 11 sample. So solving this integral for these limits, just apply these formulas. So I think in the next numerical for my band stop or my band reject filter, I'm going to show a shortcut on how to come up with this. We also have the generalized formula. So what I mean to say is there is no, the computation of these integrals are not essential if you are answering MCQ questions or your entrance exams. So where the steps are not of importance, only the answer, the final answer is what you have to mark in the MCQs. So what will happen is you don't have to do all these steps. So you can directly come up with the final expression for h of n by using the generalized formula that I'm going to show you, or the shortcut method that I'm going to show you in the next numerical. All right. So I am just solving this with the formula for integral of e to the power of j omega n is e to the power of j omega n upon j omega, and that is gonna give you what? So that is gonna give you something like 1 by pi n sine 3 pi by 4n minus sine pi by 4n. So I know this because I know the generalized formula. So I'm telling this from the generalized formula, not as the output of your integral, because solving this integral would take the application of your Euler formula. So the Euler formula is e to the power of j theta minus e to the power of minus j theta by 2j is equal to what? It's equal to 2j sine theta, right? So if it is divided by 2j, then you don't have. So it is just a sine. So when you have the negative, when you have the difference of exponential, it is equal to your sinusoid sine. And when you have the sum of your sinusoids, sum of your sinusoid, and then it is your cos. So this is your 2j sine 3 pi by 4n, and that is minus 2j sine pi by 4n. So your overall formula now, it's going to look like 1 by pi n. That is your FIR filter expression. So the questions can be obtain the FIR filter expression. So the expression is just sine 3 pi by 4n minus sine pi by 4n and over pi n. So that is the expression. But if it is for finding the coefficient, so then you have to move, you have to do more. So in order to find these coefficients, I'm going to use the Scilab, and you must use your scientific calculators in the exam. So we will write the code. I'll write a small 2-line code in my Scilab, and I'll just compute these coefficients. And again, for my, like I said, I will get for n equal to 0, I may get 0 upon 0, which is not defined or which is not a number. So I need to use my limits formula for my h of n. Good. So before we get to finding the coefficients, let me show you the generalized formula for your bandpass filter. So the generalized form for your bandpass filter is given in this manner. So h of n is equal to 1 by pi n. All right. So 1 by pi n into sine upper cutoff frequency minus lower cutoff frequency. See, so this means if the question is given, I can write this expression. I can write this from the question, because if my cutoff is here, it is from pi by 4 to 3 pi by 4, and that is exactly what my bandpass filter expression is stating. And now if my cutoff is from pi by 2 to 3 pi by 2, you can write the answer sine 3 pi by 2 minus sine pi by 2, and that is my bandpass filter. See, so from the question I can write these answers. I don't have to do these complicated integral evaluation using limits. You don't have to if it is an MCQ, but if you have an 8-mark question asking you to find the bandpass filter expression, then you have to do all these steps. All right. So depending on your exams, you can choose to how you solve these questions. So now let us find the coefficient. So after that, we move on to finding the coefficients, because in this numerical we want to find the window coefficients, and then we want to do the magnitude response. So let's do the coefficient finding here using this 2-line code in my Scilab. You can see how it relates to the equation written above it. Good. And then what I can say is just the first value. My h of 0 is plus or right. It is coming as what? Not a number, because it's 0 divided by 0. So for h of 0, what I'm going to do is I'm going to apply my limits. And this limit formula was introduced in my previous lecture itself. So I'm going to apply that limit. Theta tends to 0, sine pi theta divided by pi theta is equal to 1. So that is the formula we are going to apply here. I'm going to show it again for you. And then I can tell what will be my h of 0 will be 3 by 4 minus 1 by 4. That's going to be 2 by 4 equal to 1 by 2. That is 0.5. So let us see this. So this is the formula. Sine pi theta upon pi theta is equal to 1. And then what I'm going to do is I'm going to take your limit n tends to 0. So I'm going to apply that formula to this expression. So which means I'm having just pi n in my denominator. So I'm going to get a term. I'm going to get my 3 by 4 term, and which means I have to take that 4 by 3, and that's going to become 3 by 4. And this is going to see this. It's going to come out to be 3 by 4 minus 1 by 4. You can choose to remember it very easily, because I have only my pi n, and inside sine argument I have 3 by 4 pi n, and my denominator is just pi n, so which means I get a 3 by 4 extra in that term. For the second term, I have pi by 4n inside my sine, and my denominator is just pi n, so I get a 1 by 4 extra there. So with my h of 0 becomes then 3 by 4 minus 1 by 4, which is equal to 0.5. Good. So applying these limits, it's not much, because all the other values you will get from your calculator. You can directly apply the value of n to be, see what are the values. 0 means 1, 2, 3, 4, 5. So I have written h of plus or minus 1, plus or minus 2, plus or minus 3. So now these are the coefficients. So I have the coefficients written out for you, which were computed in the previous slide. And now I'm going to use my Hamming window coefficient formula, which is shown on the right hand side, 0.54 plus 0.46 cos 2 pi n upon n minus 1, and where my n is from 0 to n minus 1 by 2, because it is symmetric on the other side. So the negative side is minus, right, minus n minus 1 by 2 to 0. So it is symmetric on that side. So I'm doing only the computations for positive side because I cannot index the negative side. So I'm doing for the positive side, and I'm going to multiply. So my FAR window final coefficients HW of n is equal to H of n into WH of n. And if you can see here, I have a lot of zeros. So I like this question. So this question is, it makes things easier for us. So there are a lot of coefficients 0, which means I am not interested in all those coefficients. As you can see, after I multiply, so when I do the multiplication of H of W, with my window, I get only two coefficients. That is H of 0, HW of 0, and HW of plus or minus 2. The rest of the coefficients become 0. So now my FAR in H of Z, because I have to still come up with the causal form, causal stable form, and that is not going, that must not have any positive powers. So here I have Z square, which is making this filter non-causal. So the presence of Z square is making this filter non-causal. So how do I make it causal? By multiplying it with Z to the power of minus m minus 1 by 2, and that is going to make this a causal and a stable filter. So let's do that here. So this is a non-causal representation because of the positive power. So let's do that multiplication, and I get the final filter coefficient. So final FAR filter after applying your Hamming window, after inducing causality, right, is gonna look like the next equation. So it's gonna look like H of Z is equal to 0.5 Z to the power of minus 5 minus 0.2175 Z minus 3 minus Z minus 7. So I have H of 5, H of 3, and H of 7. I just have 3 coefficients here, right? It's a very simple filter. All the other coefficients, because ideally I should have 10 coefficients from H of 0 to 10. But here all these coefficients are 0, and I'm having coefficients only for H of 5, H of 3, and H of 7, because the power, the negative power of my Z tells me what are those coefficient positions. So this is, I'm going to write it here. This is your FAR filter. So the new causal order, the new causal ordering of coefficients is going to be this. H of 5 is 0.5, H of 3 is minus 0.2171, and H of 7 is minus 2171. All right. After this, what we are going to do now is obtain the magnitude response. So we have done the filter coefficients. The next step, or the next thing we have to do as part of this big question, is to plot the magnitude response. And I know the formula. I have written the formula in the first slide. I'm going to write it again here. And I'm going to apply my n is equal to 0 to 5. Right? I'm going to apply my m is equal to 11 in this formula. And then I'm going to see what is the formula, what are the expansion coming out to be. So H of m minus 1. So what is the formula? And then I'm going to use my Scilab. You guys have to use your scientific calculator. Put values of omega to, you take some 10 to 15 values of omegas between 0 to 180, and then see what you get as your H of omega, and then you plot it. So then you get your bandpass filter response. So here, why I'm not writing the full terms are because I know that my H of 0 is 0, H of 1 is 0, H of 2 is 0. So I'm not showing all those computation. I have my H of 5 value and I have my H of 3 value, and that is the only thing that's going to last in this expansion. So all the other terms are going to cancel out to be zeros. These are all becoming zeros now. So I have only my magnitude response is given by H of 5 plus 2 H3 cos 2 omega. So that is a very simple magnitude response. And then I can use this and then compute the plot. I can plot the magnitude response now. H of 5 plus H of 3 into 2 cos 2 omega. So I know what is my H of 5, that is 0.5 minus 0.2171. I'm plugging in the values. These values are the final values. These values are the values of causal and stable filters. So after applying the causality, you make use of this formula. And then you see here, I'm writing that formula there, and I'm taking omega to be values between 0 to 180, and that step omega is equal to omega into pi by 180 is has to be done in the calculator to get this response. So you have this on the left hand side, I have my h of omega, and on the right side I have my h of dB, h of omega in my dB form. And now this is your what, band pass filter. Good. So this is the response, this is the magnitude response of your band pass filter. So that is it. So we have done 3 full numericals on FIR filters. I have done the low pass filter using the Fourier series design. Then I have done your high pass filter using Hamming window and your band pass filter using Hamming windows. Now one other window that is remaining is your Blackman window. So I'm going to take this band stop or the band reject filter for h of omega is equal to 1, and then I'm going to show you how to do this. So this is the steps for my band stop filter. So the band stop filter, as you can see, it is from minus pi by 3 to plus pi by 3, and the stop band is from pi by 3 to 2 pi by 3. So I can put the generalized expression. So I'm not going to do this. So this is your take home exercise. So you finish it off. So this is the generalized expression. Thank you.